All right, everybody. What we're going to be taking a look at today is the idea of similar polygons. We will be taking a look particularly at similar triangles here shortly, but for the time being, we're going to just talk about similarity as it relates to polygons in general. So the definition of what similar polygons are is that all of their corresponding angles have to be congruent and all of their corresponding sides have to be proportional. Now, it goes without saying that if two figures have angles that are the same and they're not congruent, we can conclude that yes, the figures will be similar to each other. But a lot of times what you have to do is you won't be given necessarily uh, angles showing that all the corresponding angles are the same, but rather you'll be given a set of sides, and you'll have to compare the ratios of all of the corresponding sides in order to determine whether figures are going to be similar or not. Now, a term that we're going to start using, we're going to use it a little bit here, but we're also going to revisit it later on in the year, is scale factor. So scale factor is whatever the ratio is between corresponding sides of similar figures. And the scale factor can go one of two ways. In the example that we have here, the extra example that I'm providing you here, we have triangle ABC is similar to triangle DEF. So if I wanted to know the scale factor of triangle ABC to triangle DEF, we're going to look at the sides of triangle ABC over the sides of triangle DEF. And that's what we're seeing on the right side here, where I'm showing you the corresponding sides are proportional to each other. So what that's telling us is that triangle ABC is twice as large as triangle DEF. Now we could very easily turn that around. Let me pick a pin here. We could very easily turn that around and I could say triangle DEF would be similar to triangle ABC, and then we could reverse the ratios, and therefore we ultimately really all we do is take the reciprocal. So if the scale factor, the value that shows you how the dimensions change, if the scale factor is a number that's larger than 1, we would say that that is an enlargement. If the scale factor is a value that's smaller than 1 but bigger than 0, we would say it's a reduction. Now we can't have scale factors that are going to be negative values because it's not possible to shrink something to the point where it inverts and goes into an alternate dimension. That's a whole other breed of math and topics that we're not even going to get into. So scale factors, for our intents and purposes, all need to be positive numbers. So here what we're going to take a look at is if you know figures are similar to each other, can you identify their corresponding parts? Now, when we were talking about identifying congruent triangles, with our side, 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 side angle, side, and all that stuff, we spent a good amount of time practicing how to identify the corresponding parts, either by looking at a diagram or by how the figure is named. So for instance, by the way the figure is named, if I look here at angle A, because it's the first letter, angle D, being the first letter of the second triangle, must correspond to it. So we could look at the names of the figures by themselves, or we could look at the diagrams themselves to see which, based on their values, which angles correspond to which angles, or which sides correspond to which sides. So here, it's asking us to identify all of the corresponding angles, which is easy enough to do by either, again, looking at the way the figures are named or by looking at the diagrams. So the next part here, when it says identify the corresponding sides, well, for instance, the first two letters of triangle ABC are AB, and then we have the first two letters of DEF to be DE. And I made that one a little longer than I wanted to, so we just want to look at those two. So those two figures, or those two sides, must correspond to each other. And we're just going to either, again, look at the name or look at the diagrams to see, well, how do they work? So that's why down here in part B, we're setting up the ratios as AB over DE, BC over EF, and CA over FD. Now, the important thing that you must remember is that you have to simplify whatever ratios that you have. I have seen many times in the past where students would give me the ratios, say they gave me 10 over 5 and then they gave me 8 over 12. I would have students tell me, well, these triangles are not similar to each other because their ratios are not the same. Well, they are, you just didn't simplify them. As long as you simplify the ratios, that is the values that we have to look at in order to see, are the sides actually proportional or not. So here are the ratios of the sides. Well, they already kind of gave them to us. We're going to just write them down one more time. So at this point, go ahead and pause the video and work out checkpoint problem 1, where it's essentially what we were just doing in this example, and identify all of the corresponding angles and the ratios of the corresponding sides. So go ahead and hit pause, and when you're ready, hit play again and compare your answers with mine. All right. Now, here they're not giving us a diagram. You could easily draw a diagram based on the similarity statement that's been provided for you, but we don't need a diagram at all to know that angle Q and angle Y have to correspond to each other because they're both the middle letter of the how the figures were named. So here is the list of the corresponding angles and the ratios of the corresponding sides for this particular example. Moving on, now we're going to be looking at how to identify whether or not figures are similar to each other and what the scale factor is. In my experience, this type of question is a very popular standardized type question. We don't have the tax test anymore, and there's no geometry star test in Texas. However, this is something that I would expect to see on any kind of standardized test where they're going to ask you to determine, first of all, are the figures similar to each other? That's the most common kind of question that I see for problems like this. And in order to determine whether the figures are similar to each other, we have to primarily look at the sides. Here in this example, they're giving us all of the corresponding angles. They're demonstrating that all of the corresponding angles are the same. Well, if the corresponding angles are the same, then all of the sides should also be proportional to each other in similar figures. But 9 times out of 10, what they do is they just give you the corresponding sides, and you have to determine, are the figures similar to each other by looking at their ratios. And you have to do it for all of the sides, not just some of them. Because what I see is that some students will take a look at the corresponding sides, maybe they'll do 3 out of the 4 or 2 out of the 3, and whatever that last one is that they did not do, that one winds up being not similar to the other ones. So that's when we're looking at figures to determine similarity, the ratios of the sides, all of the sides have to have the same ratio, not just some of them. So identify the corresponding angles. That's pretty easy based on how it's named and how the diagram is given to us. So here we're just identifying that all of the corresponding angles are congruent, which is technically half of the definition of what similarity is. Now we're going to look at the ratios of all of the corresponding sides. Well, if you look at the ratios of all of the corresponding sides, they do all simplify to be the same ratio, 4 over 7. So because we have all corresponding angles that are congruent and all corresponding sides having the same ratio, we can say, yes, these figures are similar to each other, and the scale factor is that same ratio, whatever it is. So in this case, the scale factor between these two figures would be 4 over 7, at least the way that we wrote it for quadrilateral ABCD to quadrilateral JKLM. Of course, we could easily reverse the similarity statement, and therefore the ratio for the scale factor, we would take the reciprocal of it. The next example here, what we're going to be looking at is, well, pretty much what we've been doing. we're giving you similar figures and simply asking you to find the value of a missing side or a missing angle of some kind. So in this case, they're telling us triangle ABC, or I'm sorry, triangle BCD is similar to triangle RST. If you haven't picked up on it, that little single squiggle, that single wavy line there is the math symbol for similar to. And what I've circled, or what I put that red box around, that is what we would refer to as a similarity statement. There will be another diagram explaining that here shortly. Find the value of x. Well, that's no big deal. All we have to do is set up and solve a proportion through cross multiplication. Because they're telling us that the triangles are similar, we don't have to show that the sides are all proportional to each other. We can accept, because they're similar, the sides must be proportional. Therefore, we can write a proportion and solve for it. So based on how they're giving it to us, we're going to say segment BC. Well, they're looking at segment BC here. So the corresponding side in this case would be RS. So we're going to start off by writing the ratio 12 to 24. Now, they're also kind of giving us this one right here, ST, and that's the one that we're looking at. So that's the longest side of the triangle, so we're going to compare it to side CD, and that's how we're going to fill in the blanks here. Substituting the values, we're going to get 24 for segment RS and 13 for segment CD. Now, personally, they didn't do it here, but personally, I would take that 12 over 24, and I would simplify that ratio to simply be 1 over 2. The smaller numbers just simply make the math a little bit easier, but any way that you do it, you're still going to get the side that you're looking for, x, to be 26. At this point here, go ahead and pause the video and work out the next two problems that you see. Again, keeping in mind here, they're giving us a similarity statement, so we don't have to show that the figures are the same or that the figures are similar to each other. They're telling us that. So simply identify in part 2 what is the scale factor between the two figures and what is the value of the missing side, MN. So when you're done, go ahead and hit play and compare your answers with what I have. All right. Now, when I look at a figure like this, particularly because they're so generous and gave it to me in the same orientation, what I'm going to do is I'm going to try and find what are the smallest sides, because usually that's, again, the smallest numbers are going to be easiest to work with. Well, in this case, it's not too difficult to see that we have a 12 and a 15 and a 12 and a 15. Since those are the smallest ones, I would really look at those sides. Now we're looking at it from LMNP to FGHJ. So that means I would take 15 over 12 and simplify that as a ratio, which gives me 4/5, showing that it is a reduction from one figure to the next. Now we're going to set up and solve a proportion to find the value of x. So taking the 15 over 12 ratio that we had, I'm going to say 40 over x for the second ratio, do my cross multiplication, and show that x in this case is 32 units. Here, when we're talking about similarity, what we're going to start getting into is not just similar sides, but angles, I'm sorry, not angles, but perimeters, and at some point areas and volumes. Now the area and volume stuff is going to come a little later on. But let me explain what I see as a teacher. If I give you the fact that figures are similar to each other, then you can conclude that their perimeters are also going to be similar to each other. And the reason why is because, well, all of the sides, if they're all proportional to each other and the sides make up the perimeter, then it's logical to conclude that the perimeters that are made of similar segments must also be similar to each other. And that's a fairly intuitive thing. A lot of students pick up on that very well. But it doesn't hold true for every dimension that we could have in a figure. We have perimeter with figures, we have area with figures, and when we start getting into 3D shapes, we're going to have volumes. So here what they're showing you, what I'm showing you in this little box here, I'm particularly thinking about this right here. Well, the scale factor, whatever the ratio is between the corresponding sides, here's my scale factor, whatever we're saying A to B is. Well, area is not the same dimension as perimeter is. Perimeter is a linear measurement, meaning I'm just taking numbers and adding them together. So I'm saying feet plus feet plus feet plus feet, which means I have so many feet. Well, area is, say, feet times feet, which in this case, using our rules of algebra, has to be feet squared. So that extra dimension there is telling us now we've gone out of one dimensions and into two. So we can't compare the area at the ratios of the areas the same way that we would the ratios of the sides or the perimeter. So let's take a look at it like this. If we were in class right now, what I would tell you to do is either look up at the ceiling or look down at the floor. Just look at some tiles. Let's say I have a tile, whatever it is, a ceiling tile, floor tile, or just a square, that is 1 unit long. Well, all the sides are 1, so the perimeter in this case would be 4 because we add all of the sides together. Well, the area in this case would just be, well, let's say centimeters, or units or feet, or it doesn't matter. So here I would say 4 centimeters and 1 centimeter squared to denote that it's area. Well, what if we double the dimensions? Now this is 1, 1, 1, 1. Well, the dimensions, the perimeter, according to the theorem that we're seeing here, must also double, so that would be 8 centimeters. Now, looking at the area, I have 1, 2, 3, 4 square units. So 2 times 2 gives me 4 centimeters squared. The area didn't double. The perimeter did, but the area didn't. The area actually went up by a factor of 4. Well, what if it continues? Now let's triple the dimensions. So this side is 3, this side is 3, so the perimeter here is 12, and we'll just keep saying centimeters, but the area would actually be 9 centimeters squared. So if I triple the dimensions from the original one, the perimeter also triples. 4 times 3 is 12. But 1 times 3 is not 9. So what we're seeing here is that area changes by whatever the scale factor is squared. And that's a very big idea in geometry that is really one of the biggest missed topics when we're talking about similar figures at some point, where we're not just comparing, just their sides. We're not going to get into it right now, but I want to plant the seed because when we start talking about it, I'm going to refer back to this lesson and say, well, area is going to change by the scale factor squared. For the time being, we're going to stick with perimeter, but again, I just want to plant that seed for future lessons. Here's where we're going to start taking a look at how the similarity with perimeter works. Here we have 2 basketball courts. So I have 1 basketball court. Now a basketball court is just a rectangle. And we have one that's going to be bigger than the other one. The court of the new one, the dimensions of the new basketball court are going to be 20 feet by, oops, I put that in the wrong order, 25 feet by 20 feet. Now the old court had a similar shape, but it was only 16 feet wide. So here I'm going to say this is 16. Now we don't know what this is, obviously, but we do have enough information to figure out the perimeter of the new court, and I have similar sides with the 20 and the 16, so I can actually figure out what the scale factor is between them. And using the scale factor, then I would be able to figure out what the perimeter of the smaller court would be, and what the length of the court would have been if I needed to know that also. Here, when we compare them, we're going to say going from the small court to the big court, we're having a dilation of, where it's increasing in size. So the scale factor has to be bigger than 1, which is how we get 5/4. Now, what we're going to do is we'll take the perimeter of the original figure, I'm sorry, of the new figure, which in this case would give me 90 feet. And now I can use the perimeter with the ratio for my scale factor and set that up as a proportion. So here in this example, we're saying perimeter over perimeter. So we're saying the perimeter of the new one over the perimeter of the old one, and that's how we're getting that ratio. And then we'll set it equal to the scale factor of 5/4 and do our cross multiplication and show that the perimeter of the original smaller court was 72 feet. So I don't know if those are regulation sizes or not. I don't know. Now here, this is where I told you a second ago, or a couple minutes ago rather, that I would show you in a little bit more detail the symbols and what a similarity statement is. So the single wavy line means that says that they're similar to each other, and this part right here says that those figures are going to be, that is a similarity statement. So if you're asked to write a similarity statement, that's what you're going to be asked to provide. Now here we're going to actually start using the scale factor to figure out parts of other figures, kind of like what we saw in the basketball court. But in the basketball court, we are actually looking at the perimeter with the scale factor. Here we're going to be looking at just individual parts. So here, find the scale factor of the two triangles FGH2 JGK. So because I'm saying the first triangle FGH, which is the big triangle, 2, let me pick another color here, GJK, which is this triangle right here in blue, we're looking at we're going to pick a side from the red triangle and compare it to a similar side or a corresponding side of the blue triangle. And that's how we're setting up the ratio, in this case, to be 8/5. Because I'm looking at the overall length at the bottom, I'm looking at JK here, and I'm looking at FH. Ooh, it didn't change color. FH right here. We're looking at those two sides as a ratio. Now that I know what the scale factor is, we can find missing parts of the figure. So in this case, what we're going to take a look at, we're going to say, well, we're looking to find whatever the length of GM is. I'm sorry, what GL is. So its corresponding side is GM, so substituting 14 for GM, setting it equal to the ratio that we have for our scale factor, we'll just cross multiply and divide and see that the missing side is 22.4 units long, whatever those units may be. So go ahead and when you're ready, pause the video and work out checkpoint questions 4 and 5. And when you have your answers, hit play again and come back and compare your answers against what I have. All right, so hopefully you have your answers ready. Here they're telling you that the two triangles are similar to each other. So looking at the perimeter of the new one, what I'm going to do is I'm going to find what is the scale factor of the small triangle to the big triangle, because that's what I'm looking for. I'm looking for the perimeter of the small triangle. So I'm going to look at the corresponding sides, 40 and 72, to get my scale factor of 5/9. So I'm going to take my scale factor of 5/9 and multiply it by whatever the perimeter of the bigger triangle was, and I get the perimeter to be 120 units. And in the next one, I'm going to do something similar. I want to know how long is QS. Well, if I compare QS to XZ, again, I can see that we're reducing the figure. So I'm going to look at the scale factor again and see, well, the scale factor as a reduction would be 2/3. Multiplying the scale factor by its corresponding side that we're looking for, in this case XZ, gives us QS to be 26 units long. And that's pretty much it for this lesson. Making sure that Do you understand that the definition of similarity says that the corresponding angles have to be congruent, the corresponding sides all have to have the same ratio, they have to have this, so that way that's what indicates that they're proportional to each other. And whatever that ratio is, that common ratio is known as your scale factor, and we can use that scale factor to find missing things about the figure. But until next time, guys, if you have any questions, make sure you get in touch with me and let me know what they are. And take care, and we'll talk to you again soon.